Okay, so let's take a look at the boost converter. So from our last discussion on buck converters, if you were able to follow along, this is going to be a lot easier. And the magical component is the inductor. So let's try an even more simplified circuit than this. Okay, so let's say we have this circuit right here. We all know what's going to happen. Current is just going to go through the resistor, just like that. And if we plot this current with time, it's just going to be like this. Or it's the VI divided by R, which is the maximum current it's going to go through here. And there's going to be no change in time, until the battery or this just runs out of charges or whatever. By adding this magical component right here, we now get an inductor lag. So this graph is going to look the same, but we're going to have a little bit of a lag like this until we reach this point. And this is given by the slope. We can solve for the slope. And this slope is given to us with this equation. So if we have 10 volts and 10 henries, that's going to reduce to 1 amp per second of slope. That's just an example. So this is the principles of the buck. But if we put a switch here which shorts the circuit, we get so on the on period we get basically a circuit that looks like this, right? If we close the switch, we're gonna short out the circuit and it's just gonna go like that. Which means that we don't have this resistor ceiling anymore. The current in this inductor is just gonna keep building with this mathematical relation for as long as we keep this circuit like this. So drawing that current graph like this, and it would just go on forever until you burn your circuits. We now have a lot of current built up here when the switch is open. So when this path is unavailable. So the current is then gonna go like this. And if we let this inductor short out, so we're building up a lot of current here, and then all of a sudden we open this up, all of this current has to now go through here, which means that the output voltage is going to be that current times the R. And we're going to get something like this. And I'm just going to draw this out here. Okay. So this is during the off period when this switch is open. And all of this current is just going to rush through here. And that's all we've built. Well, let's say for our boost converter, we've built up a lot of current. So if we've built up, so let's just put it into perspective. So we got the slope right here. We have 10. Let's just put 10 volts here, 10 henries. So our slope is going to be 1. So 1 amp per second. And we hold this for 10 seconds. So that's 10 amps. And then we plug that into our output formula. So let's just say the resistance is 100. So that's 10 amps times 100 ohms. So that's 1,000 volts. So we've just successfully built a boost converter that takes in 10 volts and for a short moment has 1,000 volts on this side. Simply by just charging up, simply by letting this circuit short out, and then due to the inductor's inability to change its current instantly, we've been able to boost up the voltage. I hope that makes sense. This is just an intuitive understanding of how the boost converter works. I'm gonna put all of these documents on Patreon if you need to look at them or analyze them by yourself. Now imagine we keep this dance between shorting the inductor and letting it flow through the resistor. Imagine we do that at the 10 amp point. 10 amps is a lot. It might not work for your specific inductor or purpose, but just for this example, I'm making it simple. So this is, let's just say 10 amps. And we just keep switching here. We keep doing this. The dance happens here, where so this is when we're shorting the inductor, we're building up current through it. Then we make that path unavailable, and it goes through the resistor, and it kind of discharges. And it will discharge on this cycle. So the charge cycle is dt, the duty cycle times the period, and this is the off period. And just like the buck converter, we get this ripple current with an average here. And the average is what we get when we toggle the switch on and off at a specific rate where it's kept at a level we want it. So we're keeping it around 10 amps here to boost it up to 1000. This is just an example. You're not going to see circuits like that because you have to toggle it at a certain rate. So this is a boost of 100. Typically you'll just see a boost of 2 to 3 times, 4 times maybe. And you'll see why later. I'll go over the expression for the transfer function. And if you plot this graph out, you'll see why. So I've plotted the function 1 over 1 minus x, where x is just a replacement for d. And the blue shaded region is the area where x is less than 1, greater than 0, because the duty cycle cannot be greater than 1. The green line is 50% duty cycle. And what you'll see is that it'll asymptotically just shoot right up as we approach 1. So we have to stay within a reasonable region of duty cycle. And you can see that it's about 0.4 to 0.6. Kinda don't want a higher duty cycle than that. And you'll see once you start designing how you need to match the inductor with the switching frequency to make sure that you end up where your output voltage where you want to have it.